morning, everyone. Okay, so let's continue from wherever we left off. Before we get started, any questions from last lecture or the previous one and the last week? Jeet, I hope I'm audible.
Yes, sir.
Any doubts, questions?
For the FID, what will be the Hamiltonian pulse?
Okay, so your question is, what is the Hamiltonian for the pulse? In the rotating frame, we wrote that it gets transformed. If you might remember, for the pulse, it's a time-dependent Hamiltonian. We ended up transforming it yesterday. Is that correct? Then we ended up getting something like omega I Iz plus omega 1 cos phi Ix plus sin phi Iy, where phi is a phase with respect to the x-axis. Time-independent Hamiltonian. This is for the pulse in the rotating frame. Correct? So you're asking for the delay. What is the Hamiltonian? That depends upon whichever interactions are active. What are the active interactions? The interactions that you have are chemical shift and then scalar coupling. The chemical shift Hamiltonian is sum over all the Z-band terms. If you have only one spin, I is just one. If you have two spins, then you can write it as I1Z and I2Z or I and S, depending upon how you would like to write it. The summation works well with small index I, so therefore I wrote it this way. And then the scalar coupling also is a double summation over I and J, where I think I greater than J, where you have a pi J Ij 2II dot Ij. What do we mean by this? Summed over all possible scalar couplings that are feasible. Okay, I've never introduced the Hamiltonian in this full form until now, but we have ended up solving it for some cases. For instance, for the AMX system, we said that there are three scalar couplings, JAM, JMX, and JAX. And therefore, what does the summation mean? Just that all possible permutations should exist. Some of these might tend to zero just because of the dependence of the dipoles and their orientation and the bonds that connect them. Correct. So otherwise, the delay has significantly the scalar coupling and the chemical shift contribution towards it. Did that make sense? If you don't understand, let's go back a step again. This is the one-dimensional NMR experiment we are looking for. We say that while you're applying the pulse, if you're going on resonance, the only major effect that is present is the pulse by itself. For instance, if you're going on very close to on resonance, this goes to zero and only effect of this exists. Is that clear? Right? So nothing else exists. And during the delay, remember, you don't have a pulse. You just have the interactions between the spin and the magnetic field. This is the Z-band interaction, and this is the dipole-dipole interaction, which are present during that time. Did that make sense? Did that clarify your doubt on what is the Hamiltonian during acquisition or delay or whatever? There are relaxation terms which we are not writing, because to understand how is the Hamiltonian written for relaxation itself is a course which we are staying away. If you might remember a few lectures back, I said we'll assume no relaxation happens while executing the pulse program. We will see the same effect again today. If you might remember, let me go to the one-dimensional NMR experiment that we discussed maybe a couple of classes earlier. Let's see, we had this 1D NMR experiment, right? Where did we discuss it? Yeah. Do you by chance remember this discussion where we started from equilibrium, applied a 90-degree pulse for a simple system, H2O, where there is no scalar coupling, only chemical shift. You applied a 90-degree pulse, Iz becomes Ix. And then during this time that's being present, you just have chemical shift evolution that goes as cos omega it and sin omega it for the orthogonal component. Everybody recollect this, right? So essentially, what we are trying to say here, from here, we just move on to saying the Fourier transformation will give a delta function. Of course, there is an exp minus R2T, which we will negate and we will not discuss about it during the class, but it exists. And if you might remember, what is the effect of the delta pulse and the Lorentzian is a convolution. What does that mean? Basically, it does exist in the background. In the background at zero frequency, the relaxation processes do exist. And then you have a resonance that comes at omega I depending upon the offset. Then what you do is called a convolution, meaning that take every point in the spectrum, multiply all points here. So if you keep on doing it, slowly you will realize the convolution of this will result in a spectrum of the sort that we are used to. Correct? So we are kind of not including relaxation in our discussion, largely because we assume that we are looking at where would be the resonance maximum that comes up, and that's about it. Did that make sense? Yes? So just to finish off this question, because I wrote the scalar coupling Hamiltonian in a way that we are not comfortable with. So let's say we are taking three spins where A can be I1, M can be I2, X can be I3. The Hamiltonian for this would be written as chemical shift, which will be omega I1, I1Z plus omega I2, I2Z plus omega I3, I3Z. Just for the sake of simplicity, don't try writing omega 1 because that will confuse you with the pulse that is being applied. Okay, so be a little careful. Plus pi j, let's say 1 to 2 I1 dot I2 plus pi j23 2 I2 dot I3 plus pi j13 2 I1 dot I3. And if you can assume a weak coupling limit, then the I dot j component reduces itself to IZ JZ component only. So this is what we are dealing with for most of this course. We are not worrying about strong coupling limit. Weak coupling limit helps us for most of the cases. So let's just go with that. Did that answer your question on what is the Hamiltonian? How does it come during delay? This is a very important aspect on which Hamiltonian acts at which duration. And if you're able to understand this, then you will be able to do the rotations to get your final solution. Whatever we left off yesterday, we said that we started for a methanol system. We are trying to solve the density matrix for it, where we started from equilibrium. And then we said if you apply a 90-degree Y phase pulse, you can remove the garomagnetic contribution from it. You just have an Ix plus 3Sx. Then you have a time evolution that happens. In the time evolution, you have both scalar coupling and scalar coupling and chemical shift evolution that would exist. Then we also understood the aspect that if the Hamiltonian is a sum of two, then this is the propagator you're looking at, exp minus IH1 plus H2 times t. We were trying to understand, okay, how can we deconvolute the e power a plus b kind of operator? We said e power a plus b is equal to e power a times e power b or e power b times e power a if a and b commute. Basically meaning that if the Hamiltonians for chemical shift and scalar coupling commute, then it doesn't matter what you apply first. So that's the example that we took. We started from Ix, which we did expand it to the chemical shift evolution. Along Z, Ix will become Ix cos omega it plus Iy sin omega it plus 3Sx. The 3 ends up coming because there are 3 methyl protons. Therefore, Sx cos omega St plus 3Sy sin omega it. Right? Followed by that, you have J coupling evolution for each one of them, meaning that you keep this as a constant, put that right outside, because remember, here the Hamiltonian will only act upon the operators. It will not act upon the constant coefficients that would exist. Not constant, coefficients that exist. So therefore, what you end up getting here is cos of omega it times Ix cos pi jt plus 2 Iysz sin pi jt. This is what we have been saying in the past week on how, when you start with one given operator, how does it evolve? So let me also write the J coupling pi j to Izz. What are we doing here? We are doing a stepwise evolution of chemical shift only and then scalar coupling. So this part is chemical shift evolution. So now we are doing scalar coupling evolution. Sine omega it times iy cos pi jt minus 2 ix sz sine pi jt plus 3 cos omega st sx cos pi jt plus 2 sy iz. So iz sy sine pi jt. Always keep the order. Writing is, always keep it is. Don't change it si. It might confuse you as you go forward. Plus 3 sine omega st times sy cos pi jt minus 2 iz sx sine pi jt. So where are we right now? We are at the end of the pulse program, meaning that this is the evolution time t. If this is the evolution time t, as a function of this time, how does chemical shift and scalar coupling evolve is our question.
Is getting that
Until this, are you clear? Until you get ix plus 3sx, are you clear? When has it happened? It has happened after the application of the 90-degree pulse. Clear? You're having the time evolution here. And therefore, you got to understand what is the Hamiltonian at that point. The Hamiltonian at that point is a sum of chemical shift and scalar coupling. Agree? Since it's a two-spin system, the chemical shift Hamiltonian is going to be omega I omega s sz. Correct? And weak coupling Hamiltonian is going to be pi ijs 2 izsz. Since we said it's weak coupling. So far, so good. So if this is the Hamiltonian, what do you have to do? You have to do exp minus iht sigma of 1 exp plus iht. This is what is your task. So now you have the Hamiltonian as a sum of two Hamiltonians. So therefore, you have to invoke that if you have e per a plus b kind of an operator, how does that operator look? Since this is the a and b are not numbers. If a and b are numbers, you can just write e power a plus b as e power a times e power b. You cannot do that for operators because operators need not commute, because commutation indicates whether you can change the order in which you end up measuring them. So therefore, this Hamiltonian, the e power minus ihcs plus hj of t can be written as e power minus hcs times t times e power minus hj times t. We're able to write it because the hcs comma hj in this case commuted. So therefore, what we are trying to say, it doesn't matter what you operate first. You can change the order of the operators. So the e power minus ihcst times e power minus ihjt times sigma 1 times the propagator inverse can be swapped in order. So we put the, what are we doing here? We put the chemical shift term first. So let me try to write it so that it makes a little more sense. So what are we trying to do? We did, I'll just write that part here because there's no space. So what we should have done, we should have done exp minus icst exp minus ihjt sigma 1 exp plus ihcst exp plus ihjt. This is what we should have done. We are able to split it into two operators because a and b commute here. And at the same time, since a and b commute, you can change the order. So how are we changing the order? We are changing the order such that it's exp minus ihjt exp minus ihcst sigma 1 exp plus ihcst exp plus ihjt. I have just swapped this order. I kept the other one constant. Now, if you slowly observe, this is just a chemical shift evolution. Correct? So you want to have a rotation about IZ, omega I IZ plus omega S SZ on the density matrix, and the density matrix is IX plus 3SX. And I will only operate on I, S will only operate on S. So therefore, I will go as cos omega IT plus IY sin omega IT. 3 times 3 comes because there are 3 protons. The moment you have finished operating this, then you take that density matrix and operate it with the scalar coupling. That's essentially what is done. So you have the Hamiltonian, now you have the new density matrix and you're operating. So all I'm trying to say in this exercise, you could have done chemical shift followed by coupling or coupling followed by chemical shift. It's okay because the Hamiltonians commute. Did that make sense? Okay. With that being the case, what we are able to see here is that the final density matrix looks a little daunting. There are too many terms. Now the question comes up, okay, what do I find as observable? We have to go back and recollect what did we learn. We learned that the observable is going to be given by the trace of the density matrix to the operator. Can we just take IX as the operator? We'll also see IY. We generally want to see IX plus IIY, but I want to do it stepwise so that you are able to catch up. If you end up doing that, we have done this several times. We know for a fact only IX times IX will give a trace, non-zero trace. Everything else gives a traceless matrix. So this is not IX, 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 so is not this. The only term that's present with an IX is this. So therefore, only these two coefficients would exist. So therefore, you will be able to say the trace of that matrix. If you have a question, you should ask.
In the second line, that there is a 2IX SZ term. So
where is it 2? Here.
Yeah.
You tell me what will happen. 2IX SZ times IX. What do you get? What is IX square?
Identity.
Therefore, identity times SZ will be what?
SZ.
And what is the trace of SZ? Therefore, it's traceless. Right? So except for the first term, everything goes away. Right? Okay. So therefore, what you'll only have here, cos of omega IT times cos of pi jt. These are the two terms that are present. Cos of omega IT times cos of pi jt. Immediately, what you are able to observe is that you can write it as cos of omega I plus pi j t plus cos of omega I minus pi j t. Yeah. So similarly, you can take the trace of sigma with IY. Sigma with IY will be what? Sigma with IY. So you're going to get sine omega IT times cos pi jt. Right? So which is going to be, right? Sine omega IT cos pi jt. So immediately you're once again able to realize this is going to be sine of omega I plus pi j plus sine of omega I minus pi j times t. Okay, so far so good. So therefore, what are you able to realize is that the trace of the density matrix with respect to I plus operator therefore will be, you're going to have a combination of things that are going to exist, right? So go back and do this. You're going to have an I here. So you're able to realize you're going to have an exp I times omega I plus pi j times t plus exp I times omega I plus pi j times t plus exp I times omega I minus pi j times t. Okay, take it, enjoy. We are not worrying about any prefactors that exist. Don't worry about it. We are only looking at proportionality. So if that is intriguing, so let's write it as proportional. So is that okay? Yeah. So therefore, what you all are immediately able to realize is that if you end up doing a complex Fourier transformation, this is going to give a delta function at omega I plus pi j. omega I minus pi j. This is going to give a delta function at omega I plus pi j. Is that correct? So therefore, what you are immediately able to appreciate is that you're going to get a spectrum with plus pi j, omega I plus pi j, omega I minus pi j as the resonances for the spin I, and therefore this is going to be 2 pi j. Right? So similarly, go back and do the steps that would end up coming for something like this. I have not done the entire coupling part. You cannot just do it once. You should actually start doing it multiple times, because you're looking at only I spin here, which means that you're looking at the hydroxyl spin of the methanol. You have to do the coupling evolution again and again, where nicely the scalar coupling would end up coming. Here, yet again, you're able to see the scalar coupling comes up as plus minus pi j, which is the doublet that it splits into. Since it's a CH3, you got to evolve the coupling 2 more times in addition to the time that I've done, which will nicely give you the triplet that's present for the hydroxyl proton. Okay, largely because you're not immediately going to get cos pi omega plus pi j and omega minus pi j. You're going to get cos of sine, then you put them together to get whatever is desired. This is why I requested you guys to do it, where repeated evolutions, the scalar coupling has to happen. You can always write the density matrix in its full glory. For instance, this is the entire term that's present, correct? You know the operator representation of Ix and Iy Sz. It will be a 2x2 or a 4x4 matrix. It'll be a 4x4 because you have 2 spin half systems, right? And now it's an IS3 spin system. It'll be even more bigger than that, right? It's just not going to be a 4x4, which is going to be much bigger because you have S3 is there. So you cannot just deal with simple AX versus AX2. You realize that you increase the spin system by 1 more spin half. So it won't be a IS spin system is 4x4. IS2 will be an 8x8. IS3 will be a 16x16. So instead of worrying about how the matrix representation of each one of this looks, do you realize that we quickly went into how the spectrum looks? If you are able to understand and accept that the formalism we have generated is self-consistent, where we'll quickly pick the terms that's going to give us a signal, we move on to the answer. Do we see that? We don't obsess ourselves with literally writing the 16x16 matrix. Do we agree on that? So from here on, that's how we are going to end up continuing. Okay, so let's take another example. For instance, let's take a very simple example. We'll not solve this because it's very easy to think about it. Let's say that you're having a 13C1H spin system. And previously we saw a proton experiment. Let's see, we are looking at the carbon experiment. There's a carbon one-dimensional NMR experiment. Previously, I didn't define it as a proton one-dimensional NMR experiment. Since we ended up measuring protons, we can say that this was a proton one-dimensional NMR experiment. More specifically, it's a 1-pulse one-dimensional NMR experiment. 1 pulse indicating you have only 1 pulse for an excitation, and 1-dimensional NMR because you're having only 1 time dimension to Fourier transform. Similarly, we can also look at a 1-pulse carbon-13 NMR experiment. The only difference here is that you still have an IS spin system. Generally, proton is given I and carbon is given S. The less gyromagnetic ratio spin is given S, while the higher one is given as I, generally. So this is yet again an IS spin system. Without even solving the density matrix, I'm sure you guys would agree, the resonances that are going to end up coming would be delta of C plus pi j Hc and plus delta of omega C minus pi j Hc. You have seen the IS spin system over and over again. Is that correct? So therefore, the carbon 1D NMR signal will be split by the carbon proton scalar coupling. Good. So remember, while the scalar coupling gives you good amount of information for the proton spectrum, where you will be able to find how many partners are there and therefore say what moieties you're dealing with. The carbon NMR spectrum, it just reduces the resolution. Why do we say that? We would be able to find what is CH, CH2 and CH moieties in some other experiment. But otherwise, what you're able to realize is that the carbon sensitivity itself is low because the gamma is low, the abundance is low. So splitting a signal, remember, the half portion that the person from Pune made me realize. So we have a half, right? Everything splits. The moment you have scalar coupling, you're going to get reduction of intensity. Area under the curve has to be conserved. Therefore, when a single resonance splits into two, you're going to reduce intensity by half. Carbon is already insensitive. Now with proton coupling, you're going to reduce sensitivity further. So generally, a carbon experiment is done with something called proton decoupling. Don't ask me how it works. It will make things complicated for the time being. Maybe we can see it after the medicine. What it will do is to not allow the scalar coupling to come up. Basically, it will decouple. It will act as though the proton spin alpha or beta cannot be distinguished. So this way, the decoupling helps. So how will the pulse program look? It will have an additional element called decoupling, where during the acquisition, you will decouple. There are additional things that go with the carbon NMR experiment where decoupling will exist throughout, which we'll try to see after midsem. But it suffices to say that if you do a carbon NMR experiment with a 90-degree pulse, although you should get scalar coupling with respect to proton, you don't want the scalar coupling to evolve. You only want the chemical shift of the carbon. This helps you improve sensitivity and resolution. How does it improve sensitivity? The doublet becomes a singlet and therefore the intensity increases. How does it improve resolution? If there are two closely resolved spins or two closely spaced chemical shifts, now they're all going to split and you're going to have overlap between chemical shifts, which will confuse you. Now all that will be minimized. Does that make sense? So the entire process of decoupling helps a lot. Yes.
When we draw two separate channels, that means you're looking at two separate parts of the frequency.
Excellent. Yes. So basically, let's take a 400 megahertz NMR instrument. Proton will be at 400 megahertz. Carbon will be at 100 megahertz. Very good point. So these are two separate channels. It's similar to the fact that you have two radios, one radio to listen to say 98.3, another radio to listen to 91.4, for instance. Because their frequencies are that different, you will be able to tune specifically to each one of them. So you'll have specific receivers for carbon and proton. Whenever you receive carbon, you cannot receive proton from the same coil. Whenever you're receiving proton, you cannot receive carbon from the same coil. Okay, so you can selectively listen to proton or carbon. On the other hand, for the methanol example, although I just wrote for the I spin, S spin will also be received, by the way, because these are all proton channels. So there you will collect the signals for I and S spin system together. But if it's a heteronuclear IS spin system, you will separately get the information from the carbon and the heteronuclear channel. Sorry, proton and the heteronuclear channel. Yeah, good question. So that's how a carbon 1D NMR experiment works. So slowly, I think we have equipped ourselves to understand how does 1D NMR work for proton and carbon, how the 1D proton gives us chemical shifts, scalar couplings, and integrals. What are integrals here? Area under the curve. If you have the spectrum that comes up, you end up integrating the NMR resonances. They are quantitative in a way where if you have 3 protons, it will integrate to 3, 1 proton will integrate to 1. Basically, the ratio of 3:1 for methanol. Similar integration will not work very well for carbon. We will not discuss why that comes up. But overall, it does make sense that we end up decoupling proton from carbon spectrum so that you get a high resolution and sensitivity. There's one more small point. While we ended up saying carbon will have proton splitting, we are not worrying about the fact that carbon might have carbon split. Can somebody answer me why is that we are not worrying about carbon-carbon splitting in an ethanol sample at natural abundance? How will this look? This will look as 13C, 13C, 1H, 1H. We said that, okay, if I'm acquiring this carbon, I can decouple this proton to get a singlet. But why are we not worrying about neighboring carbon-carbon 13 spins at natural abundance?
So since the natural abundance of 13C is very low, it's much more probable that it's a 12C right next to it. So
that's correct. What is 1% of 1%? 0.01%.
Yes.
Right?
Yes.
So therefore, if you have natural abundance of 1%, good answer. If you have natural abundance of 1%, the probability to find two neighboring carbons as 13C is 1% or 1%, which is very small. So already carbon is insensitive. You're not going to see something as small as this. There are experiments to enhance this. Let's not go there. But overall, what we are able to realize is that if you have a molecule that you have synthesized, proton and carbon NMR can be acquired in a way to get chemical shifts, scalar couplings as desired, and the quantitative information from the integrals. Yeah? Everybody comfortable? Good. And I hope we are able to appreciate the fact that we can use the semi-classical picture and the density matrix based formalism to understand all this. Now let's go to a important aspect. Let me do inversion recovery. What's an inversion recovery experiment? It's still a one-dimensional NMR experiment, but we'll have a pulse program that looks like this. This is a 180-degree pulse. We can have it along, say, Y. And then this is another 90-degree pulse. We can still have it along, say, Y. And then what do you have in the middle? You have a tau delay. And this is something called the interscan delay. Basically, you can assume that you're starting from equilibrium. So slowly I'm starting to draw pulse programs where these are the RF pulses. Anything that I draw thin is a 90-degree pulse. Anything that I draw fat is a 180-degree pulse. Okay. Yeah. Let's try to understand how what will be the outcome of this experiment. Let's start with a simple eye system. Like water. It's not very easy to do this for water, but let's take, let's say, 1% water in D2O solvent. Can we take this as an example? Right? So what will be the initial density matrix? And it's just going to be IZ, omega I IZ, but there's only one spin. Who cares about the proportionality? We can write it as IZ. The reduced density matrix will be IZ. Right? The first thing that you're doing is a 180-degree pulse along the y-axis. Therefore, the density matrix will become minus IZ. You're just inverting, nothing complicated. Then you have a time duration tau. Can any one of you tell me what will be the Hamiltonian of this during this tau duration? It's water. What all interactions are present in water? Only chemical shift. And therefore, what will be the Hamiltonian? Omega I IZ. So therefore, what is going to happen during this tau evolution to this density matrix? Nothing. Okay, so it remains minus IZ, right? We'll understand what it is doing a moment later. And then you have T duration, sorry. And then you have a 90-degree pulse along Y. Go back and think about it. Therefore, it will be minus IX. You started from Z, you apply a 90-degree along Y, it will be plus IX. You started from minus Z, you apply the same 90 along Y, it will be a minus IX, right? And you have tau duration, during which only chemical shift will evolve, Hamiltonian tau. So you're going to get minus IX cos omega IT minus IY sin omega IT. So we have started from the equilibrium density matrix and finished up in the final density matrix where you will be able to get the chemical shift evolution. Then you might ask, hey, why did you entirely waste time by applying the 180-degree pulse in the tau duration? Does that make sense? You could have achieved this only with this module. Why are you wasting time with this additional 180 degrees and tau module? One important aspect which I said, don't worry about it, is the thing that will play a role here. If you end up applying a 180-degree pulse, from a semi-classical picture, what do you think is going to happen after you have applied?
Relaxation.
Slowly come back. Exactly. Relaxation will happen. Longitudinal relaxation would happen. So therefore, what is going to happen? The length of the vector will slowly keep changing as a function of time, which we are not including in this part. So in reality, there will be some relaxation that would have happened. And what type of relaxation is it? It's longitudinal or transverse? It's longitudinal. So only R1 relaxation would have played a role. Does that make sense? You have seen the simulations where if you're able to achieve a perfect 180, you won't get anything transverse. It nicely goes back up. So therefore, if you have the ability to repeat this experiment such that tau is changed, say, at 0 seconds, 10 milliseconds, 50 milliseconds, 100 milliseconds. For instance, I'm just giving some random numbers. 250 milliseconds, 500 milliseconds, 1 second, 2 seconds, 5 seconds, 10 seconds. If you're repeating the experiment 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, Okay, there are 10 experiments here where the tau value is set to one of this and an experiment is acquired. So therefore, what are you going to have? You're going to have 10 1D NMR experiments, which are slightly going to vary at the chemical shift based on the intensity. The intensity will keep changing. When you had 0 milliseconds, that is the maximum negative signal you would have been able to acquire along IX. Why negative? Because you take IX times minus IX, you get a -1, minus cos omega. So the -1 will just invert the signal into negative. So what is going to happen? This is going to have a large negative this thing. This is going to be slightly small, slightly smaller. Maybe it will be 0 crossing there just for an instance. Then you have slightly positive, and then positive. And the length of this and this would be equal. The magnitude of this would be equal because almost at 10 seconds, it would have fully relaxed, completely come away. Then it just acts as a 90-degree pulse experiment. That makes sense? So if you guys end up plotting the intensity as a function of this tau period, you're going to get something of this sort. You would be able to fit this parameter to judge what is the T1 time of water. Did that make sense? This experiment is called the inversion recovery experiment because you inverted the polarization and slowly asked, how does it recover? How quickly does it recover? Therefore, are you guys able to accept the fact that if you have different chemical molecules that you have synthesized, you can repeat this experiment to get the T1 times of different species, right? That's how people end up measuring T1. Okay. So from simple 1 pulse, 1-dimensional NMR experiment, we have gone to 2 pulses, 1-dimensional NMR experiment. Agree? This is a 2 pulse, 1D NMR experiment. Still, it's 1D. Okay, so the number of pulses does not determine the dimensionality of the experiment. The dimensionality of the experiment is determined by how many time domains do you Fourier transform. Until mid-sem, we'll only bother ourselves with a 1-dimensional NMR experiment, nothing else. Let's understand this completely so that we can understand multi-dimensional NMR experiments. Okay. The previous example we saw had only the 90-degree pulse and acquisition. So that is a 1 pulse, 1-dimensional NMR experiment. Here you have a 2 pulse, 1-dimensional NMR experiment. And the purpose, why did you include the second pulse and the delay, is to measure the T1 value. Slowly, what you're able to see is that, oh, if I have the handle on changing things, I can measure things beyond whatever is directly measurable. Right? So let's do the next type of experiment. This is one of the landmark experiments in NMR spectroscopy. It's called the spin echo. As I said, we are moving away from 1 pulse, 1-dimensional NMR experiment. Now, this is an experiment where you have a 90-degree pulse and you have a 180-degree pulse and you have tau durations in the middle. Okay? And then final acquisition, small t. Generally, anything that's written in capital T or tau indicates it's a constant delay, meaning that the values are kept constant. On the other hand, wherever you write small index, like small t, indicates that it's a variable time. How much you acquire depends on you. Yet again, we'll see how those things get decided after mid-sem. Okay, so anywhere you see a small alphabet, it indicates an evolution with respect to that. Anywhere where you see tau or a capital T, that indicates a constant time duration. Okay, so this is an experiment where you start with a 90-degree pulse and followed by a tau delay, then a 180-degree pulse and a tau delay again, and acquisition. Can we try to understand what is the outcome of this experiment? Can we still keep our life simple and look at water molecule, which just has a single spin? Let's try to understand as many things from water and then slowly complicate from methanol, ethanol, and whatever, protein. Yeah. What is going to be the initial density matrix, reduced density matrix? IZ. So from now on, if I end up writing an arrow with something, indirectly, what do we mean by this? The arrow indicates an evolution with respect to minus IHT, where in this case, the H is going to be omega-1 tau p times the phase. Let's say we are applying along the Y phase. Slowly, what we are doing is condensing whatever we wrote for pages together into a small arrow. Are we okay with this convention? This indicates what is the density matrix you're starting with. This indicates what is the propagator that you're working on. The arrow just indicates where does it end up. In the background, you're thinking about, oh, you're solving the Liouville von Neumann equation for an initial density matrix with a time-independent Hamiltonian. Because we know that for pulses and delays, the time-independent Hamiltonian, how is it given by? That's what we did yesterday, right? So therefore, what is this going to become? This is going to be plus Ix. Everybody okay with it? Now, in this tau duration, we have seen several times, we only have chemical shift evolution that's going to happen, correct? Only chemical shift evolution because nothing else exists for water. So what is this going to become? Ix cos omega it plus Iy sin omega it. Not t, tau. Followed by this, the next step what's happening is that we are applying a 180-degree pulse. What phase do you guys want? X or Y? Okay, I'll take Y. Therefore, what is going to happen? If you end up applying along the Y phase, Y component will not change. Everybody agrees with that because you're applying along the vector itself. No change will happen to the vector. On the other hand, the X component will change. So it's going to go to minus Ix cos omega it, tau. Yet again, you have a tau duration yet again, you have a tau duration where chemical shift evolution happens. So I'm going to quickly write cos of omega I tau times Ix cos omega I tau plus Iy sin omega I tau plus sin omega I tau Iy cos omega I tau minus Ix sin omega I tau. This is why I was requesting you guys to practice the BCH expansion and the propagation so much that do you see that when we start with something, we quickly write it without thinking much because I'm basically applying the rotations in my head. So this is why the math formalism was important because we can go to the answer quite swiftly. So basically what you end up getting here is that you have a Ix cos square omega it with a negative sign, right? And you have minus Iy cos sine, and you have plus Iy cos sine. So therefore, we are able to see that this gets cancelled. Everybody agrees? These are just two opposite entities that are present, given the coefficients. And you're going to have a minus Ix cos square of omega it, tau, and minus Ix square sine minus Ix sine square omega I tau. So therefore, this entire thing reduces itself to, is it 2? Let's add numbers to this. This is 0, this is 1, this is 2, this is 3, this is 4. So we are looking at density matrix at position 4. So it just reduces itself to Ix cos square omega I tau plus sine square omega I tau, which is just going to be minus Ix. Yet again, we spent so much amount of time having the tau 180 tau that's being present, and all it did is, instead of applying a 90-degree Y phase pulse, if you apply 90-degree minus Y phase pulse, you would have gotten minus Ix. So why did we waste this tau 180 tau duration? Yeah, so there are multiple things that we learned from it. Let's ask learning outcomes. What you learn is that a tau 180 tau module refocuses chemical shift. What is happening is that this module, tau 180 tau module, in general, when you have a delay, evolution happens. It could be chemical shift evolution, scalar coupling evolution. You're taking a simple system where only chemical shift is present, so that only that can evolve, correct? Given that there is a delay, what you would have alternatively expected, chemical shift should evolve. But putting this 180-degree pulse in the middle seems to have somehow magically negated the effect of chemical shift evolution. During this 2 tau period, chemical shift did not evolve. It is as though chemical shift did not evolve. Do you see this? Yeah. So this is one of the important outcomes where a tau 180 tau module will refocus chemical shift, meaning that for most of the cases, you don't have to evolve chemical shift in a tau 180 tau period. Now, did that make sense? A tau 180 tau period refocuses chemical shift. What is the second learning outcome? As much as we did bother about relaxation, longitudinal relaxation in the inversion recovery experiment, similarly, in this given experiment, do we agree, since you have generated a transverse magnetization, you agree that the spin-spin transverse relaxation will be in effect? So during this tau period, what is spin-spin relaxation? You have generated a coherence, which looks like a bulk magnetization. How does the coherence die? The dephasing happens for each of the alpha beta states. So you can imagine this as the magnetization also slowly loses coherence, and therefore it dephases and gets a random phase in the XY plane. This would exist in the absence of pulse, because you're being perturbed, you're in a non-equilibrium state, you want to go back to equilibrium. That's relaxation. So therefore, following the application of the 90-degree pulse, which generated the non-equilibrium state, this delay will try to take the non-equilibrium state back to equilibrium, which is the relaxation process. Since you have generated transverse magnetization, it is going to be spin-spin relaxation that's going to happen. Let's ask, how will this tau period affect this decoherence? If the longer the tau period, do you agree that it will dephase a lot more? Correct? If you have very short tau period, it will dephase a little bit, but the 180 will refocus it back. We will see animations for it. I have also uploaded in the classroom. Please go and take a look. Okay? So therefore, this module potentially helps measure T2. How would we do this? Yet again, take tau as 0, 10 milliseconds, just giving some examples, 20 milliseconds, 40 milliseconds, 60 milliseconds, 80 milliseconds, 100 milliseconds, 150 milliseconds, 200 milliseconds, say 300, 500, and maybe 1 second. Slowly, you also realize that I'm carefully making a choice for tau delay for transverse relaxation, which is vastly different from the T1 measurement. We know for a fact T1 is much longer than T2. Therefore, the time delays have to be carefully measured to fit the curve. So similarly, if you're able to measure the intensity as a function of the tau period, what do we get? Let's say this is the tau period that you're measuring it for, varying the tau as a function of time. You're going to get signal that is going to decay. Take the signal maximum and plot it. And then if you end up fitting it, you will be able to get the R2 rate from it for every given spin. Is that correct? You take the water, change the tau, slowly change the tau. You'll keep on reducing the intensity because as you have longer and longer tau, it's going to dephase more and more. Right? It's going to decay more and more. That can never be recovered. Did that make sense? Yes or no?
So if it's dephasing, that's getting refocused, right? So what do we lose?
Chemical shift will get refocused. Relaxation will not get refocused. Chemical shift refocusing happens. It'll be as though basically the tau 180 tau did not do anything to chemical shift evolution. It didn't happen at all. But on the other hand, for the length of the vector, we are talking two different things here. How much does the vector move as a function of time versus what is the length of the vector as a function of time?
That's also in the transverse plane itself.
That's correct.
That's also going to get inverted and recovered.
It will get recovered, but not fully. If the tau duration keeps on increasing, think about it. How are you going to generate a coherence without application of a pulse? The work done is not going to be entirely efficient doing it. Okay, let's see a simulation for it. Maybe it will make more sense. So this is the example. I'm literally taking it out of Wikipedia page. So this is where you end up starting. That's your equilibrium state on the top left in the A panel. You end up applying a 90-degree pulse. They are nicely showing in terms of the red dot where which part you're looking at. You see that the vector ended up coming to the transverse plane. Then during this tau duration, you see that the magnetization slowly starts to dephase itself, right? Based on chemical shift evolution also, but I'm only talking on water. Let's put water on resonance. So what's only going to happen? The dephasing happens, indicating that it's losing coherence, right? And then they're trying to show what will happen if you apply the 180-degree pulse. It's literally taking the dosa and completely flipping it on top, right? So anything that is moving this way, if you ended up flipping, will start to face back up. So chemical shift gets refocused that way. But unfortunately, the length of the vector can never be recovered. You still lost time. Therefore, the length of the vector is going to keep reducing, right? So therefore, overall, the effect of what you did from B to F has no chemical shift information encoded in it. If it had chemical shift information, the vector would have moved a little bit with respect to time. The evolution somehow got negated due to the tau 180 tau. On the other hand, the relaxation got taken care of it. So since we are running out of time, what I request you guys to do is to go back and take a look at this block simulator. Yeah, we have seen this several times. I'll go back to equilibrium. Small point, how do they do the simulation is that when will the dephasing happen? When the magnetic field is not very homogeneous. If it's homogeneous, the dephasing will not happen, right? You have a B naught. We said the B naught is constant. The B naught is variable. You realize the Larman precession frequency of each of the spins are going to be different. Therefore, the dephasing will happen therefore. Okay. So therefore, what they suggest is that you go to an inhomogeneity based simulation. You apply a 90-degree hard pulse. So slowly as a function of time, there's going to be fanning out of these vectors that happen. Okay. You apply a 180-degree Y phase pulse or any phase pulse. You just inverted everything. Keep watching. There'll be a time where all the vectors would bunch up, equal to the time we let it evolve. Okay, so there you go. Slowly bunching up. It has bunched up and the chemical shift evolution got lost. So let's do the simulation again. Let's go back to equilibrium. Now, let's do one small thing. What is the small thing that we want to do? Instead of being in the stationary frame, which is having too much precession going on, let's go to the rotating frame. So now you understand the application of the rotating frame. Let's see the same example. Let's take inhomogeneity to be the case. I'm going to apply a 90-degree hard pulse. Since I went to the rotating frame and I'm on resonance to this, I'm only going to see dephasing that's going to happen. So watch. Yeah, only dephasing happening. And how are the vectors fanning out? They're going in a certain direction, right? I apply the 180-degree pulse. It's coming back up. And exactly in the time that I allowed earlier, if I give the same amount of time, they'll all be refocused. That's the effect of a tau 180 tau. You can imagine this as relaxation that happens, which should reduce the length of the vector, which we'll see in a moment, or chemical shift refocusing that happens. Did that make sense? Yeah. So okay, there you go. And after that, it started dephasing. So you can keep doing this exercise again and again. Why is it called an echo? You realize that the signal keeps dying. Keep watching. Now the signal is building up. And then it goes back. It's like an echo. You give a sound, it goes and comes back, right? So it builds up and dies. That's how an echo behaves. So that's why it's called a spin echo. Spin because the nuclear spins are being exploited. Now, before we wrap up, let's quickly take a look where the relaxation also exists. Okay, I'm going to go back to equilibrium. Are we ready for the simulation? Go to inhomogeneity, still be in the rotating frame, apply a 90-degree hard pulse. Dephasing is happening. In addition, the reduction of length of vector is also happening. Okay, you might not be efficiently able to see it. Let's do a 180-degree pulse again. Chemical shift refocusing would happen, but unfortunately, the length of the vector is also slowly reducing. That can never be recovered with this experiment, depending upon the time tau. Okay, as you keep changing the time tau, it's going to, if you keep increasing the time tau, the length of the vector keeps reducing. And therefore, if you end up picking the intensity and plotting it as a function of time and fitting it, you will be able to get the R2 relaxation. Did that make sense? So therefore, slowly starting from density matrices, we are able to understand how one-dimensional NMR experiment would give its outcome in terms of chemicals of scalar coupling. In addition, since you have the density matrix formalism, slowly you're also able to understand the fact that you'll be able to build up additional pulses to extract more information from your chemical moiety, which is like T1 relaxation or T2 relaxation, and therefore have an idea how does a chemical moiety look.